Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad IZZUDIN bin KAMARUZAMAN. Our group will be present the experiment file, which is the tip cylinder. For the theory, pressure vessels are containers regardless that store or transport any kind of the fluid at a pressure. Okay. The theoretical treatment of the tip cylinder assumes that the hook stress and the radial stress are not constant across the thickness at the cylinder wall. Okay, and then we consider a tip cylinder with the inner radius R1 and the outer R2 with the internal pressure P. Assume plane stress condition. The elastic stress at any radius R are given by the Lamb equation. Okay, for the Lamb equation derivation, we have the Hook law. Sin elasticity V, E and stress Z and volume are constant. Therefore, stress theta plus stress R equal to constant. That's for the equation 1. Then we substitute equation 1 in the equation, so we get stress R equal to A minus B over R2. Okay, where A and B are constant, and then the equation that we get, we substitute in the equation number 3, and then we get the stress theta equal to A plus B over R2. So the equation 2 and 3 are known as the Lamb equation.
Okay. My name is Muhammad Ridhuan SYAKIR bin Muhammad ROSHDI. Metric number is AD180021. Next is observation. First, the cylinder is ensured at zero pressure when the handwheel is checked to turn freely. Second, the value in the SM1011 software are always fluctuated. 3. The pressure value is increasing below maximum allowable test pressure. 4. The reading is taken while the value is paused in the software. 5. The internal pressure in the tip cylinder is setting at 2 MPa by using handwheel. 6. The maximum allowable test pressure is at 6.89 MN per meter square, and the length of the bending beam is 203 mm. Thank you.
Hi, Assalamualaikum. My name is NAZAHAH NUHA binti ABDULRAHMAN. I will be presenting for the result and also calculation. So for the result, we have two tables, which is first to measure and calculate the strain gauge value, and we have 13 gauge number, and the radius that we use is 18.5, 28, 36, 45, 56, 63 and 75 millimeter. So for the first radius it is 28 millimeter at the first gauge number, and starting by the hoop strain, the measured strains we got is 20.4 times 10 power of 96, while the theoretical strain is 18.1 times 10 minus power of 96, and the error difference that we got is negative 2.3. And at the second gauge number, at the same radius, for the radius strain we got at the measure strain is negative 20.7 times 10 power of 96, while the theoretical strain is negative 15.73 times 10 power of 96, while the error difference is 4.97. So next, as in the table shown. For the table 4 is derived and theoretical stress value. We use the same radius as in the table 3, and we calculate for the derived and theoretical, and the derived we calculate for the hoop strain and also radius strain, same as in the theoretical strain. So starting by the radius is 18.5 millimeter. At the derived for the hoop strings, the value we got is 3.1313 mega Newton per meter square, while the radius range we got is 1.03 mega Newton per meter square. For the theoretical for the hoop strings, we got is 2.26 mega Newton per meter square, while at the radius range is -2 mega Newton per meter square. So next, as in the table shown. So proceed for the calculation. In this calculation, we define for the three value, which is theoretical strain, derived stress equation, and the theoretical stress equation. So let's proceed for the theoretical strain. In this theoretical strain, we find out for the value at the hoop strain, radius strain, and also longitudinal strain. So first, for the hoop strain, the formula that we use is hoop strain is equal to P divide by 1128.2 times 10 power of 3 times 1 plus 5625 divide by R square minus by 0.33 times 1 minus 5625 divided by R square. For the example, is when P is equal to 2 mega Newton per meter square and radius is equal to 28 millimeter. So after we key in all the value inside into the equation, and the value that we got for the hoop strain is equal to 18.10 times 10 power of 96. For the radius strains, the equation that we use is equal to P divided by 1128.2 times 10 power of 3 times 1 minus 5625 divided by R square and minus 0.33 times 1 plus 5625 divided by R square. For the example, as the same value in the hoop strings, is P is equal to 2 mega Newton per meter square and the R is equal to 28 millimeter. So after we key in all the value into the equation, we got is negative 5.92 times 10 power of 96. So for the longitudinal strain, the equation that we use is quite different than the hoop and also radius strain, which is equation is equal to negative 2.925 times 10 power of negative 7 times by P is equal to pressure and times 1 plus 5625 divided by R square minus 0.33 times 1 minus 5625 divided by R square. For the example that we use is when P is equal to 2 mega Newton per meter square and the radius equal to 75 millimeter. After we key in all the value into the equation, and the value that we got is negative 1.17 times 10 power. So for the derived stress equation, we define two equations, which is hoop stress and also radius stress. For the hoop stress, we use is hoop stress is equal to E divided by 1 minus V square times by V times by hoop stress, radius stress plus radius strain plus hoop strain. While in the radius stress, we use equation is E divided by 1 minus V square times by V times with hoop strain plus radius strain. And as in the example, we use when E, which is Young modulus, is equal to 73.1 giganewton per meter square, and the V is equal to 0.33, and at the radius of 28 millimeter, that we got the value, which is the hoop strain, the radius strain is equal to negative 20.70 times 10 power of negative 6, and at the hoop strain we got is 20.440 times by 10 power of negative 6, and at the equation of the hoop stress, after we key in all the value, the hoop stress that we got is 1.11 meganewton per meter square. While for the radius stress, after we key in all the value, we got is negative 1.15 meganewton per meter square. So for the theoretical stress equation, we find out the value for the Hooke stress and also radius stress, same as in the derived stress equation. But the equation quite different, which is the Hooke stress we use is equal to P divided by K square minus 1 times by 1 plus R, the second R square minus by R square. And for the radius stress is P divided by K square minus 1 times by 1 minus R, the second R square divided by R square. And the example is when P is equal to 2 meganewton per meter square and the K is equal to 4.054, and the second R is the diameter for the second diameter is 150 millimeter, and to get the radius we have to divide by 2, and the value that we got in the radius, second radius, is 0.075 meter, and the radius that we use is 38 millimeter. And for the Hooke stress, after we key in all the value, we got 1.06 meganewton per meter square. And for the radius stress, after we key in all the value, we got the value is negative 0.80 meganewton per meter square. So that's all from me, and thank you.
Hi, my name is Muhammad ISMAIL FAWZI, and I'm going to talk about the discussion for this topic 5 of thick cylinder. So firstly, we need to plot the graph of the experimental and theoretical Hooke and radius stress against 1 over R squared. So after we have done plot the graph, we can see that for the theoretical and derived of Hooke stress based on the yellow line and based on the orange line, we can see that there are not so many differences in the values, but there is still a fluctuation in the middle of the line. We can see there. And for the theoretical and derived of radius stress, we can see that there is some difference which is quite significant in the plotted graph. We can see the line fluctuate, and also the value are sometimes the values are not the same. Next, we need to compare and comment the experimental value with the theoretical value. So after we have done the experiment and we have taken the value, so when we about to compare the value, we can see that there are some noticeable differences of values and some are not. Back to the previous video, I have already explained that there are some noticeable difference and some aren't, and maybe this is because the error that occur might be because of different sources when doing the experiment, such as like the thing that usually happen, incorrect measurement taking methods and tool errors. Okay, when usually the value differences happens due to we're not taking the measurement precisely. So when we handling the experiment, we need to be more precise to prevent the fluctuation of the values to occur. Thick cylinder are usually applied or used in oil truck or boilers, or maybe storage tanks and pipes in industrials. Thick cylinder is usually used to transport liquids, or maybe to hold it, as to store it. So due to the liquids or the fluids, anything inside it are usually in a condition of high pressure. So thick wall cylinders are usually able to withstand that high pressure and temperature so that they won't fail. And when they usually fail, we can find out that the fracture of materials are usually in a ductile condition. And we can see the ductile fracture of materials as it has a conventional elasticity and also high strength.
Hi, my name is IZZAT bin BADRIN, and I will be concluding our experiment, which is the thick cylinder. In conclusion, the main objective of this experiment, which is to demonstrate and analyze the stress systems in a thick cylinder, is successfully achieved. Also, the types of stresses, which are radial stresses, hoop stresses, and longitudinal stresses, were determined. Other than that, it is found that when the radius increases, which is from the inner radius to the outer radius, both radial stresses and hoop stresses decreased. And last but not least, the Lam's equation for thick cylinder stress distribution theory was successfully derived. Throughout the experiment, human error and equipment error is taken into account. Human error occurred when reading the gauge values, thus contributed to the error differences between measured and theoretical values. So our recommendation to overcome this error or to minimize it, we need to make sure that the people who are responsible for clicking the hold button to always focus on the value of the pressure shown in the software so that the results obtained are more accurate. That's all from me. Thank you.